Hello, YouTube. How's everyone doing? Today we're going to be doing a continuation for our matrix and vector norm examples in numerical analysis. So last time we looked at a infinity norm, and yeah, I guess let's just start. So first thing we're going to do is this very interesting thing called Cauchy Schwarz. I'm praying I did not butcher that name. As well as the Holder inequalities. Cool. And so this guy is from two mathematicians, Cauchy from France, I believe, and Schwarz from Germany. Yeah. And cool. So we're going to start with what it is. So we could say computing, and we're going to first look at Holder actually. Computing matrix, P norms with P equal, or computing matrix P norms with P not equal to 1 or infinity is more difficult. And to approach this problem, we note that inner products can be bounded using P norms. Cool. So this is actually pretty cool. We'll go more into detail. So just understand the idea that inner products can be bounded. So I think that's a big takeaway from that. Satisfy 1 over P plus 1 over Q, which is equivalent to 1, and with 1 is equal to P and Q greater than or equal to infinity. That is the worst infinity I've ever seen. Okay, not much better, but I'll take it. Then we can say the holder, and I don't know what those two dots over the O are, so if anyone knows, please leave a comment. I would really appreciate that. Yeah, so that'd be awesome. So then the Holder inequality states that for any vectors such as x and y, we can say, and we're using adjoint in this a lot, so say the absolute value of x adjoint P, or you could just try to think of this as, I'll explain this in a second. And this is obviously norms. Okay. And yeah, that is the Holder inequality, guys. So with this in mind, the Cauchy-Schwarz is, let's go with that. Cauchy-Schwarz, or Cauchy-Schwarz. And Cauchy-Schwarz, we're going to say for this is P is equal to Q, which is 2. So thus, sorry about that, X adjoint Y nice. Now, yeah, duration of these results. And just wait for me to finish writing this, guys, and we'll come back to this. Can be found in, you know, linear algebra texts. Both bounds are tight in the sense that for certain choices of X and Y, the inequality become equalities. So please take a moment to, oh my gosh, I'm so sorry. Terribly sorry about the technical difficulties. My camera fell. Anyway, so here we have the whole thing we want to look at. So please look at that. Awesome. And now we can take a little bit more of a dive into what is, I guess you could say, the Cauchy-Schwarz inequality. And so this, basically one takeaway we saw earlier that I said to look at was how inner products can be bounded. Now that's kind of huge. So this, in a sense, is try to think of it as a magnitude or a size, because it's the absolute value of the inner product. So try to just imagine that, and keep in mind the inner product. So remember what that definition really means. And then these, of course, are norms representing length or even magnitude, in a sense. So this was from another fellow YouTuber named The Bright Side of Mathematics. Totally check him out. He does absolutely wonderful stuff in regards of analysis. But he goes through a whole proof, which is like 15 minutes, but we're not going to go into that. We're really just going to look at this guy right here. And it was just the whole idea of what Cauchy-Schwarz is. So like I said, we have an inner product. Yeah, for all X, and yeah, so our inner product, and we can say, is less than or equal to that. So what does that mean? Think of the magnitude of each of these. Or you could even say that, you know, here is less than or equal to this guy. And I think that's a really good way to look at the Cauchy-Schwarz. That this is you know, typically less than or equal to that. So yeah. And if they are equal, then we can also determine that they are linearly independent, or dependent, I'm so sorry. And here we can also regard this as the size of the inner product, as well as just size and matrices of the, or size and magnitude of the vectors. But yeah, I think this is a really good description of Cauchy-Schwarz. So now that we have this guy, let's take a further look at another example regarding vector and matrix norms. All right. So next up we have example 2.5. And we're going to name this the 2 norm of a row vector. Cool. Now, consider a matrix A containing a single row. Not too hard to imagine. This matrix can be written as A is equal to A adjoint, where A is a column vector. Cool. The Cauchy-Schwarz inequality allows us to obtain the induced matrix 2 norm for any x we have allows us to obtain the induced matrix 2 norm, and then we can say period. For any x we have a matrix times a vector 2 norm, which is equal to a 2 norm I believe that's order, but it could be raised. Therefore, we have a norm 2, which is equal to supreme or suprema. And this is just your standard in regards of matrix norms. Another way it can be written out. Which is also equal to a 2. Cool. And yeah, this is also proven due to the Cauchy-Schwarz. So that is pretty freaking cool, you know? And we can also look at it like this for yeah. This is another way I want to show you. In case y'all can imagine this, this is what we need. And yeah, that's it. Cool beans. All right. Next example is I'm not gonna lie, I'm more of a pen guy, but pencil's good too. Example 3.6, the 2 norm of an outer product more generally consider the rank 1 outer product A is equal to U, yeah, we can say UV adjoint, where U is an M vector, and I'm praying y'all know what outer product is a n vector. So it's 2 vectors. An outer product is basically just 2 vectors that make a matrix. I believe, and I think that's like 90% of what it is, so we're good. For any n vector x, we can bound the matrix vector 2 norm as follows. Yeah, so just consider an outer product in regards of that. And yeah, we're just gonna figure out a different way to write this guy, so cool. And so like we said, we're gonna do our x included in there. And because we have that, well, hold up. This is a little bit tricky here. Yeah, we can pull this guy out. My goodness. I'm so sorry, y'all. I am very sick right now. A little bit of a cold going on. Got the music. So, let's get one of these bad boys. Like, dang. Okay, sorry, y'all. Back on with this guy. We can break this up like this. Yeah. And then that should be perfect. And And we can say that because of a Cauchy Schwarz. My gosh, I'm so sorry because of that right there. And this just stays. Okay. Cool. Anyway, this I actually really like this example a lot because it kind of connects everything pretty nicely. Therefore, a norm 2 is less than or equal to u norm 2, v norm 2. And again, this inequality is an equality consider the case as where x is equal to b. And cool. So this was a really beautiful example, I think. Runs through everything nicely. And yeah. Next up, we're just gonna look at a little bit of a property and I think end it there. Bounding the norm of two matrices multiplied by each other in an induced matrix norm. And induced is just 1, 2, and infinity norms pretty much. So the induced oh my gosh, like my spelling sometimes I don't even know where it's going. The induced matrix norm. Oh, this is moving a lot, I'm so sorry. Induced matrix norm of a matrix product can also be bounded. We can say that by letting x norm, or not x norm, norm L and norm M and norm N, and those can just be any norms, be on complex region of L, complex region of M, and complex region of N, respectively, and let A be an L times N matrix, and B and M by N. So we have three norms on the complex plane, and let A be an L by N, L by M, B be an M by N, and for any x in the complex region of N, Cn, which is 1, we have this guy. Uh-oh. Just imagine a vector there. Cauchy Schwarz back at it again. Oh, actually, no, I'm so sorry. Very similar layout, though.